Hi there, welcome to Labster. Today we will learn and explore Newton's first law of motion. This law was verified by experiments and observations for over 300 years and explains many phenomena we observe in our everyday life. This simulation uses voiceover. Using the lab pad is an important way to get the most out of this simulation. Is this the perfect? Then let's get started with your first mission. Our virtual lab will allow us to think out of the box and do things that normally we can only imagine. For this simulation I want to travel back in time with you and reach out to Newton himself. In fact, who would be better to explain his first law of motion? Click on Newton's book to travel back to 1687. We officially traveled back in time to 1687. This is fascinating, don't you think? Newton is right there, in his studio. Let's go talk to him. Click on Isaac Newton to start talking to him.
Hello, I am Isaac Newton, but who are you and why are you wearing strange clothes? You seem like you're from a different time, or maybe I am just delirious. It's all that Apple's fault. Since it fell on my head I have big memory troubles. I wrote some theories that I no longer understand, they seem out of their time, difficult. You seem out of my time also, so perhaps you can help me.
Oh dear, it seems that Newton forgot what he was working on. This is unfortunate. However, we might contribute to his most famous discoveries and help him remember. Let's start by reading what he last wrote on his book. Click on Newton's book.
The last thing I wrote before the accident is: a body will remain at rest or keep moving in a straight line at constant speed unless it is acted upon by a net external force. I would really appreciate it if you could help me clarify this statement.
What Newton just read is his first law of motion. Let's help Newton through experiments to clarify what he wrote. Before doing that, there are some things we need to address. Let's shake off some dust from Newton's memory by replying to a first question. If there are two forces going in the same direction, how would you find the net force? That's right. In fact, the net force is the sum or the difference of all the forces acting on a body, depending on whether they have respectively the same direction or the opposite direction. Now that we know a bit more about the net force, we can investigate whether there are any forces acting on a body at rest. This way we will test what Newton wrote in his book on this matter. Select the forces that are acting on the hockey puck which is at rest on the table. Press the Ready button to verify your answer. Press the Help button next to it if you feel lost at any point. Here's your hint. The hockey puck has weight, and the table prevents it from falling. Good job, you selected the correct two forces acting on the body. We have the weight force, which pulls the object downwards, and the normal force exerted by the table. These forces are balanced, therefore they do not change the motion of the body.
We have learned an important concept here. If a body is at rest, like a hockey puck on a table, the net force acting on it is zero. However, this does not mean there are no forces acting on the body. I wonder if this property also applies to a body which moves in uniform motion.
No sooner said than done. I have replaced the hockey puck with a ball that rolls in uniform motion on the table. But first, I want to ask you a question. Which of the following motion is uniform? That's right. In fact, if an object is traveling at a constant speed and it is moving in a straight line, then it is moving in uniform motion. I would have loved to use an airplane for our next experiment. Unfortunately, I don't have an infinite lab in which the plane can keep moving forever in uniform motion. Instead, let's use a snapshot of a ball rolling in uniform motion. Select the forces that are acting on the ball which is moving in uniform motion on the table. Press the Ready. Here's your hint. The ball is rolling with a constant speed. This means that the forces acting on it are balanced. Ding ding ding. You are a natural. Also for the ball we have the weight force, which pulls it downwards, and the normal force exerted by the table. What is the net force acting on the ball? That's right. This is another important piece to add to Newton's first law puzzle. In fact, even though a body moves, if its motion is uniform, the net force acting on it is zero.
I feel much better now that we clarified what it means for an object to be at rest or in uniform motion. But there is still something I need to clarify. No matter how hard I try, I do not recall the meaning of the word inertia. Since I have used this word very often in my book, I assume it must be important.
Let's play again on the table and see if we can learn more about the inertia of a body. Place the 1 kilogram cube on the frictionless surface. Press one or more arrows and adjust the values on the slider to strike the cube and reach the duck within 5 seconds. Be careful not to make the duck fall off the table. Amazing! You hit the target in less than 5 seconds without compromising the duck.
The experiment we just did reminded me of something. The tendency of a body to resist changes in its state of motion can be overcome by applying a force. Ah yes, I called this property inertia.
What does the inertia of a body depend on? That's right. Let's look at this property by increasing the mass of the objects. Remove the 1 kilogram cube and place the 10 kilograms cube on the frictionless surface. Press one or more arrows and adjust the values on the slider to strike the cube and reach the duck within 5 seconds.
Well done. Shall we try with the heaviest cube?
Remove the 10 kilograms cube and place the 100 kilograms cube on the surface. Press one or more arrows and adjust the values on the slider to strike the cube and reach the duck within 5 seconds. Well done! You successfully completed the task also for the heaviest cube.
Hey, did you notice that the 100 kilograms cube is the one that needs the biggest force to reach the target? Why is that? That's right. A more massive object has a greater tendency to resist changes in its state of motion, and therefore a bigger inertia. Thank you for clarifying the concept of inertia. You know what? I think I will call my first law of motion the law of inertia. It sounds just right. I am wondering how things are going to change if we add friction to the system. I remember that friction is the force resisting the motion of a body. However, I cannot clearly recall what are the practical consequences of this force. I have a question for you. Which of the following statements about friction is not true? That's right. Would you mind playing with different surfaces? I would like to see how the body will behave if we apply a force.
Remove the frictionless surface and replace it with the asphalt surface. Strike the 10 kilograms cube with enough force to reach the duck within 5 seconds. Well done! Now remove the asphalt and place the glue surface under the 10 kilograms cube. Strike the 10 kilograms cube with enough force to reach the duck within 5 seconds. What a winner! Notice that you needed to apply a bigger force with a glue surface in order to reach the duck. This is because the glue has more friction than asphalt.
Now that we know more about friction, I want to bring our experiment on a higher level. I want to stop a body in motion by applying a force.
Move to the other table. Stop the 10 kilograms cube within the halo zone. You will need to apply two forces by selecting the two arrows. The force from the left will give the body a push, while the one from the right will help you stop it. The second force will be applied once the cube reaches the halo zone. Make sure the cube doesn't bounce, and press ready when you are all set.
We made it. Did you notice this is nothing but my first law? In fact, the body would have continued to move with uniform motion forever if we had not applied a counterforce to stop it.
Remove the frictionless surface and place the asphalt surface under the 10 kg cube. Well done. Try again to stop the 10 kg cube within the target zone. Click ready when you are all set.
Good job you there. This is very interesting. It seems that if you use a surface with friction, you need less counterforce to stop the cube. I cannot figure out why though.
Why you need less force to stop the 10 kg cube with a surface with friction? That's right. In fact, the direction of the friction force is always opposite to the direction of motion of an object. For this reason, friction resists the object motion and therefore, you need less counterforce to stop the body. You have got a great understanding of this, so I think you are ready for some calculations. Let's go. Imagine you have a body at rest on a surface that exerts a friction force of -5 Newton to the left. If there is a force F1 of 50 Newton pushing the body to the right, what is the force F2 you need to apply so that the body will remain at rest? That's right. With a force of -45 Newton to the left, you will balance the forces so that the net force acting on the body will be 0 and it won't move.
Thank you for refreshing my memory on my first law. The fog is now starting to fade. However, I still have an intriguing curiosity to satisfy. Do you think my law is valid also in space?
I think we should just go to space and find this out. Luckily I brought with me a spacesuit from the future. Click on Newton's open book to teleport in.
I can't believe we are in space. It's like floating, I feel weightless. I believe gravity drastically reduced. By the way, I really like this spacesuit. It has so many buttons, I wonder what this one does.
Oh no, you just pressed the nitrogen jet thrusters. But don't worry, I'll let you move just for a little while and then I'll grab you. Meanwhile, observe how you stayed at rest until the thrusters were activated, even if just for a moment. And look at you now, you are moving in uniform motion in space.
Hey, this was fun. I activated the thrusters again in the opposite direction, and I managed to stop. If I hadn't applied an external force, I would have continued floating forever.
After this experience, do you think that Newton's first law of motion is valid also in space? That's right. It's not that the laws of motion are any different on Earth than in space. Good job you there.
I am glad my law still applies in space, but what forces were acting on me while I was floating in uniform motion?
Press the arrows to select the forces that were acting on Newton after activating the thrusters for less than 1 second. Press Ready to verify your answer or Help if you feel lost at any point. Remember we are in space, far from Earth, and the thrusters were activated just for a moment, before Newton started moving in uniform motion. Press the arrows to select the forces that were acting on Newton after That's right. Here we are far away from Earth's gravitational field, so we may say that gravity is so small we can neglect it. As a result, here in space, we have been able to experience uniform motion in the absence of any force.
I am so glad you came with Dr. One from the future today. Thanks to you, my first law of motion has no more secrets for me. Hope to see you soon to continue investigating our universe together.
Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.